lecture 33. In this lecture we will discuss network functions. Actually, in any network, what we need basically three essential components. One is your network, second is your excitation to the network, and third component is your response from the network. Okay, this is basically in time domain. So once I know, for example, the network and excitation, let's say it is two-port network. Once I know the network, excitation is given to it, I can compute the response at particular branch, in particular branch, maybe in terms of current or voltage. Okay. So RT, how can I obtain? I can obtain by the convolution between the excitation given to network with the impulse response. Let me define impulse response as h of t. Okay. This is in time domain representation. Now, if I would like to go it into the Laplace domain, so to study the network function, in Laplace domain we can write the same convolution equation as R of s, which is the Laplace transform of R of t, equal to E of s, that is the Laplace transform of excitation, multiplied with the Laplace transform of the network function or the impulse response, we can say, that is N of s. Okay, so from that I can write the network function will be equal to R of s divided by E of s. So here we can see that it is the ratio of the Laplace transform of response to the Laplace transform of excitation, and condition is there, the network or circuit has to be initially relaxed. This is very important condition to define the network function. Means all the initial conditions are 0. Okay, so this way you can define the network function. Now let us categorize the network function. Basically, the network function can be categorized into two ways. One is called a driving point. The driving point may be your impedance, or driving point may be your admittance. Okay. So what is driving point? So to clear this, suppose I have the network like this. Okay, and here if I would like to compute driving point impedance, basically driving point impedance can be defined as the Laplace transform of response, which will be in terms of voltage, and excitation is current. Okay, and this has to be measured from the same pair of terminal, then only that is called as driving point. Understood? So driving point is that where I am measuring the response and current from the same terminal, then that kind of thing, that kind of network function is called driving point network function, or driving point impedance, or driving point admittance. And let me combine this two words, so this is called as driving point emittance. Okay, so driving point emittance is that where I can compute either impedance or admittance from the same pair of terminal. Fine, that may be the response may be your voltage and excitation may be current, or a response may be current and voltage may be excitation for the admittance. Okay, the next category for the network function can be defined or can be categorized into transfer function. And transfer function is that where I am computing the network function from two different pair of terminals, like this. This is some circuit from one terminal I am applying excitation, other terminal I will take it as the response. So if I am taking the ratio between the response to the excitation from two different terminals, then that kind of thing is defined under network function called transfer function. So again, transfer function can be your impedance transfer, or can be your admittance transfer, or it can be your dimensionless. So in dimensionless category, it will come the ratio of voltage and current. So that will be voltage ratio and current ratio. Okay. So these are the different types of the network functions. Okay. So let us see the example to illustrate each network function. So suppose I have the network like this. To this current source is given, then there is a resistor and in parallel with here impedance with capacitance, inductance with capacitor, and say this is my, let me write in terms of Laplace domain. So suppose Ig of S current generator, this is R, this is SL, and this is 1 over Cs, and suppose I would like to measure this V0 of S. Okay. So first let me define the driving point impedance. So this is the example for the driving point impedance. So for that, what I would like to obtain, I would like to obtain Z, which will be the ratio of the response V0 of S divided by the excitation current Ig of S, and that I have to look from the same terminal. So let me look from this terminal. Okay. So what will be this? This will be V0 by Ig of S will be what? It will be simply R plus SL plus 1 over Cs. Is it? So it will be R plus SL plus 1 over Cs. Okay. No, not SL, L and C are not in series. They are in parallel form. Okay. So it will be R plus SL over Cs divided by SL plus 1 over Cs, and we know that what is the resultant if L and C are in parallel, its impedance will be S square LC divided by S square LC plus 1, not S square LC, but basically it is SL, because this CS and this CS will get vanished. Okay, so which resultant will be R S square LC plus R plus SL over S square LC plus 1. Okay, so this way you can compute the driving point impedance. Similarly, if I want to compute the driving point admittance, it will be simply the ratio of, or it is the inverse, that is 1 by Z. Now let us take the example for the transfer function. So first let me calculate the impedance transfer. Okay, so we will take the same circuit here, consists of current generator, then there is a resistor, and then inductor followed by capacitor. Okay, and suppose this is in Laplace domain only, I will write Ig of S R SL 1 over Cs, and I would like to calculate impedance. So let me take, this is my output voltage or response as V0 of S. Okay, so current will flow in parallel form, that is this and this, and how can we obtain the V0 of S, or V0 of S will become here Ig of S into the impedances which are in parallel SL Cs, okay, because this is current here Ig of S. So what will be V0 of S? Simple, this current into this impedance. So SL is in parallel with 1 over Cs, and we know V0 over S upon Ig by S, it will be again same, that is SL over S square LC plus 1. Okay, so this is my impedance transfer. Then third example we'll see regarding the admittance transfer or transfer admittance. Okay, so here what I will take source as a voltage source, then the circuit is same R, then there is an inductor, and then there is a capacitor. Okay, so this is Vg R SL 1 over Cs, and this is IC of S. Okay, this is IC of S, for example. Okay, So what I have to obtain? I have to obtain the admittance transfer. So this transfer admittance can be obtained if I will be able to compute IC of S upon VG of S. Okay. So what will be in order to know IC of S, I should know what is the total current here. Let me call this I of S, and this I of S. Okay, first IC of S will be equal to I of S, okay, into SL divided by SL plus 1 over CS. And what is my I of S? I of S will be VG of S divided by R plus SL parallel with 1 over CS. Okay, so that simply you can compute by substituting I of S as VG of S divided by R plus SL in parallel with 1 over CS into SL divided by SL plus 1 over CS, and VG of S I'll substitute here, so it will be IC of S divided by VG of S is equal to this, okay, which is 1 by R plus SL over S square LC plus 1 into SL into CS divided by SL S square LC plus 1. Okay, so this is my transfer admittance. Now next let me calculate the voltage ratio transfer and current ratio transfer. Okay, so to obtain this, let me obtain a dimensionless transfer function. So suppose first voltage ratio let me obtain. So this will be, say, voltage source and same network L, and this is 1 over CS, okay, R SL, and this is 1 over CS, and suppose this is my VG of S, which is voltage generator, and let me compute this voltage V0 of S. So to get it, voltage ratio transfer, to come we have to compute V0 of S divided by VG of S, okay, and this will be how much? V0 of S will be equal to total, again you can use the current division rule here, so V0 of S will be total voltage is VG of S into SL impedance, SL parallel with 1 over CS divided by sum of resistances. So SL in parallel with 1 over CS divided by R plus SL in parallel with 1 over CS. Okay. So that way we can write V0 of S over VG of S, which will be equal to this SL parallel with 1 over CS, which is some impedance equivalent impedance divided by R plus that equivalent impedance. Okay. So this is your voltage transfer function or voltage ratio transfer function. Now let me take it for current ratio transfer function. Current ratio transfer function, this was voltage ratio transfer function. Okay, so for that let me take the current generator for the same circuit, R, L, and this is C. Okay, and suppose this is my IG of S, SL, and 1 over CS. Okay, and say I am interested to compute current ratio transfer function. So what I have to obtain? I have to obtain, let's say, IC of S divided by IG of S, as I am taking this from two different terminals. Okay, that's why it is the transfer or transfer function. Okay, so what will be IC of S? It will be total current here is IG of S into SL divided by SL plus 1 over CS. It is simple as that. Okay, so IC of S upon IG of S will be S square LC over S square LC plus 1. Okay, so this way we can compute the network function. Okay, so overall what we have obtained from this, what the network function consists of. So the network function consists of the ratio of the response R of S over excitation E of s, or I can write from that the response will be equal to network function into excitation E of s. Okay, so from this network function also we will get some polynomials in numerator and some polynomial in denominator. Similarly in E of s also I will get it polynomial in numerator and polynomial in denominator, right? That is for excitation also. Okay, then what can be done to compute? Basically what I need to compute r of t. So in order to compute r of t, what is to be done? I can apply the partial fraction expansion here. So if I apply the partial fraction expansion only for network, for I it will become ai is upon roots s of pi, plus similarly for the next E of s will be same, aj is divided by s plus pj's over all j. Okay, and this pi's will be the natural frequencies related with the network, and this pj's will be the natural frequency related with excitation which you have been applied. Okay, so here again one more thing is there is some restriction on the roots of the denominator. The roots of the denominator must have to lie on the left hand side of the s plane. So reason that we'll see quickly. Okay. Okay, so this is the way to define the network function. Now let us define two new words called poles and zeros. Okay, so in basically circuit theory, your network function, to define this, let me start with the network function whose application in circuit theory. The network function which I will be getting, that will be always real and rational function. Okay, so what is the rational function? Rational function is that which is the ratio of polynomial in numerator and polynomial in denominator. That's it. That is my rational function. And what is polynomial? Polynomial is the finite series. Okay, it is a finite series, and where the power of the variable has to be integer, and this will be positive integers. Okay, so for example, if I am taking my polynomial, my say equation is s raised to minus 1 plus s raised to 2 plus s raised to minus 3. So this is not basically polynomial, but if I write 1 over s square plus 1 over s cube, and then I'll get it polynomial in numerator and polynomial in denominator, because here the power of s should not be negative, it must have to be positive. Okay, or again if I'll say e raised to x, it is the infinite series. Okay, s square upon 2 factorial like this, so this will not also come under polynomial. But if I'll say like this, the 3s square plus 4s cube plus 8s and all, so here I observe that the power of the variables are positive integer, that's why this belongs to the polynomial category. Polynomial. Okay, now the network function always has to be real in circuit theory. Okay, and what is real polynomial? Real polynomial is that in which the polynomial is real for the variables. Okay, for example, the real function is, the function is real which is real when the variable is real. For example, if s is my variable, say s square 8s plus 3, so this is my real polynomial. As opposite to it, if I mention 8 3js plus 8, then this is not a real function. Basically here it consists of imaginary part. Okay, so this is the reason, that way you can define the real function. And basically if you see in circuit theory application, your network function will always be real and rational. Why? Because as we know, how can we write the problem of nodal analysis in matrix representation? It will be admittance matrix into voltage vector, which will be giving me the current vector. Okay, or in terms of impedance, if I write for mesh analysis, what it will be, it is the in matrix form, it will be the product of the impedance matrix into current, which will be equal to your voltage, independent voltage source, right? And this, if I would like to write, what it will be z11 z12 like this for number of meshes. Okay, this will be z21 z22 z2n, Similarly, it may go up to Zn1 to Znn. Then this will be these are the mesh currents I1, I2, etc. to In, and this will be equal to the independent source voltages for each mesh. Okay, now this is okay. This is, so we have to obtain it. Now basically what will obtain network function will be this way. Okay, in this matrix. So all this Z11, Z22, Zn, as already we know, these are the self impedances. These are the all impedances will be, means this will be the sum of all impedances in that particular mesh. So at least if you take it any circuit or any network, what kind of impedance it will consist of, that impedance will be always max, at most it will consist of resistor, inductor and capacitor. So what are the its impedances? It will be SL plus 1 over CS. Okay, and if I will solve, I'll get it polynomial, something RCS plus SL plus 1 over CS. This will be in polynomial in numerator and polynomial in denominator. So this will be always rational, and also this will be finite polynomials, and the values of R, S and R, L and C will always be real. So there is no question of the imaginary value of the component. That's why again the network function will always be real for this circuit theory application, if I specify the problem this way. Okay. Now let me define the poles and zeros. Once I know, okay, my network functions are real and rational. Okay, so now I can write the network function, which will be equal to polynomial in numerator and polynomial in denominator, which is nothing but rational network function. And this can be write in a generalized form, say, which will be, suppose, Bm s raised to m plus Bm minus 1 s raised to m minus 1. I am writing in generalized form. So B1s plus B0 divided by what it can be, An s raised to n plus An minus 1 s raised to n minus 1 plus A1s plus A0. Now in order to do the simplification, or in order to find out the roots quickly, what I want basically the highest power of S always has to be 1. Okay, so that means leading coefficient, try to make it 1. And how can we do that, and what is the reason? Because with that my root calculations will be easy. So for that I will divide Bm in numerator and An in denominator. So this, there will be modifications in the coefficients in numerator as well as denominator. So it will be, let's say, B dash m minus 1 s raised to m minus 1 plus b1 dash s plus some b0 dash divided by s raised to n plus an minus 1 dash s raised to n minus 1, like this, plus a1 dash s plus a0. And this can be categorized as, or this can be written as some constant k into, now once I know the polynomial, I can easily get the roots. So roots will be, suppose, s minus z1, s minus z2, like this, s minus zm over, again the roots in denominator also, s minus p1, s minus p2 till s minus pn. Okay, and with this I can write as the running product for i's will be s minus zi's, whereas divided by the running product of s minus pj's, say for j's. Okay, so overall network function which was real and rational has been expressed as k into product of s minus zi's divided by product of s minus pj's. Okay, now from this it will be very easy for me to define what is the meaning of pole and zero. Okay, so let us define the term pole. So pole is the value of s by which your network function will blow up, or your network function will become infinite. So if you look at for which value of s my n of s is becoming infinite, when I will put it s is equal to pj here, so at that time my network function will be infinite. Okay, so all the values of pj's are the poles. Okay, means the roots of the denominator are nothing but the poles, and that is represented with the symbol cross in S domain. Okay, this all I am talking about S domain. Okay, independent variable here is S, or the domain which I am talking is related with S, that is in Laplace domain. Okay, and what will be 0? Zeros are the values of S for which my network function will become 0. So if you look at this, for which values of S my n of S will become 0. So if I'll substitute S is equal to Z i's, so what will happen? Your network function will become 0. Okay, so what will be the zeros? All Z i's will be the zeros, means the roots of numerator belongs to zeros. Okay, and the symbol for representing zeros are circle. Okay, so this way we have defined the poles and zeros. Now once we know the poles and zeros, now let me put some restriction on the poles. So what are the restrictions, or what is the restriction on pole? Let us discuss. Basically, suppose I will take it the network function like this, n of S is equal to say 1 over S plus 3. Okay, so this also can be written as the ratio of response, that is R of S upon excitation E of S, which will be 1 over S plus 3, right? And then I want response R of S, and I want the response in time domain. So R of S can be written as 1 over S plus 3 into E of S, right? And suppose excitation is unit step I have applied to the network. So what is its Laplace domain? It is 1 by S. So how can I write it? It is 1 over S into S plus 3. Let me use the partial fraction here. So A upon S plus B upon S plus 3. So what will be my R of t now? R of t will be A plus B into e raised to minus 3t into U of t. So here what we can see that what input I have applied to the network, unit step input I have applied to the network. Okay, and what kind of response I got it? A plus B raised to minus 3t. So how will be this? This will be something like this. Okay, which will be 0. Fine. No, not 0, because this is due to A. It will be somewhere. It is basically 1 minus a raised to minus 3t will come, so it will be something like this. Okay, yeah. So here what I have observed, okay, if unit step function is bounded or unbounded, it is bounded here, okay, because it is having the lower limit and upper limit. So what is the response I am getting? I am getting the bounded response, which is also having the limitation in the magnitude. Okay, so it is having lower limit and upper limit for the magnitude. Okay, fine. Now here what I am saying, if I am giving bounded input, what kind of output I will get it? I am getting bounded output. Let us see the situation. R of S is n of S is equal to, say I'll take it 1 over S minus 3. Okay, so this I can write as response will be equal to 1 over S minus 3 into E of S. Say E of S is the network, same, that is unit step I have applied to the network. So what I can write? 1 over S into S minus 3, which is A upon S plus B upon S minus 3, and what will be the response? R of t will be A plus B into e raised to 3t multiplied with U of t. Okay, so just look this equation very carefully. What I have done here, to the network I have applied the excitation as unit step, and which is bounded because it is having lower limit and higher limit. Okay, and what kind of output I am getting? R of t, I am getting this sum A, B, e raised to 3t, and e raised to 3t means exponentially increasing. And how will it be? It will be like this. Okay, it will be something like this. Okay, so it is not converging. Okay, so there is no limitation, or there is no upper limit. Okay, so this will be infinite magnitude. Means what? I am applying bounded input, but am I getting bounded output? No, I am not getting bounded output. So this not satisfy the bounded input bounded output criteria. Okay, so if the network doesn't satisfy the bounded input bounded output criteria, means that network or that circuit for which my pole, this 1 over s minus 3, for which my pole whatever I got it is lying on the right hand side, means what? That network is not stable, that network is unstable, and this is the reason that the poles must have to lie on the left hand side of S plane. Okay, so how can we plot in S domain the poles and zeros? Suppose I have now the transfer function n of s is like this. Let me write here. So n of s, my transfer function is s plus 2, s plus 1 over s plus 4, s plus 6, s plus 8. Now I would like to plot these pole zeros in S domain, means I would like to show what is my pole zero diagram. So it will be at minus 1 there is 0, minus 2 there is a 0, then s4, s plus 4, s plus 6 and s plus 8. This is suppose 6. Okay, so at 4 I have the pole, means represent with cross minus 6 and somewhere minus 8 also. Okay, so this is called as pole zero plot. If the poles are real, then that will lie on the real axis. If they are complex conjugate, then they will lie somewhere here, because this is my sigma axis and this is my j omega axis. This is already, we know it in S domain. Okay, so this is the reason that poles must have to lie on the left hand side of S plane to bring the stability for the network. Okay, now we are familiar with poles and zeros. Now let us define the proper and improper transfer function or network function. Proper and improper network function. So suppose my network function n of s is equal to p of s upon q of s, and let me define the degree of numerator is m and degree of denominator is n. Now I can have the three conditions, right? What may be that? First, the degree of numerator may be less than n. Then what may happen? Degree of numerator may be equal to n. And third situation, what may happen if degree of numerator may be greater than n. So let us see all the three cases. So now suppose n of s I have, and I said okay, my degree of numerator is less than degree of denominator. So for this, let us, I got it. Assume this is my polynomial p of s in numerator and polynomial and denominator q of s, and the degree of numerator is less than degree of denominator. So in this situation, what will happen? I can directly go for partial fraction, and I can write the roots s plus p1 b upon s plus p2 etc etc. If they are real and distinct, I can write p1 p2 p3. If they are complex conjugate, I can write a upon s plus p1 plus b upon s plus p1 complex conjugate of it. That way we have solved that problem. Okay, and then simply I will get it into the exponential forms. I can use the standard inverse Laplace transform pair, and I can write maybe exponential decreasing form. I may get it, or some damping sinusoidal or sine cosine. That way I may get. Okay, this is first thing. So this kind of network function if I have, then it is called as strictly proper network function. Okay, strictly proper network function. This is first condition. Now second, suppose I have a network function which is p of s upon q of s, and then suppose the degree of numerator is equal to degree of denominator. So in this case, I cannot directly go for the partial fraction. I have to divide numerator by denominator, and then I have to write it in some quotient plus remainder upon divisor. Okay, so q1 of s. Okay, and here I'll get a strictly proper transfer function. Means the numerator degree of p1 of s will be obviously less than degree of q1 of s, and this will be my constant. Now if I am taking the inverse Laplace transform, what is the inverse Laplace transform of k1? I will get it some k1 into delta t plus this will be as good as this. Okay, so what I observed here, I am getting the impulse function, which is not at all good. Okay, so if the network I have, and if I have obtained the network function where I obtained the degree of numerator is equal to degree of denominator, then assume that there is a presence of impulse, okay, and which is not good as we have discussed. Then this kind of thing is called the proper transfer function, not strictly proper, but it is proper transfer function. Then third category is, say I have a network function which is P of s upon Q of s, and assume that degree of numerator is greater than degree of denominator. So if I divide numerator by denominator, and if it is greater, obviously I'll get it one polynomial k1 of s plus, then next is quotient plus, no, this is quotient plus remainder upon divisor, that is q1 of s. This will be strictly proper now, but here k1 of s will consist of the terms in terms of s with its power, maybe s plus 1, maybe s square plus s plus 2, like this, plus strictly proper transfer function. Now if I'll take the inverse, so what I can observe here is that I will get it the impulse plus the derivative of impulses, okay, because of s or s square factor, okay. So if the degree of numerator is greater than degree of numerator, then I will get impulses and its derivatives in that particular network function, okay, fine. Okay, with this let us take it one example from FFQ. Suppose I have the circuit which consists of current source, then there is a capacitor, resistor, and then there is an inductor. This C R L, and say this is my I of t, okay, this is I1, and this is my V naught t, and inductor is given 1 Henry. So first question is find V0 of s divided by I of s, which is what, which is, now I am taking V0 of other terminal, I of s is at one terminal, so this will be my transfer impedance, okay, transfer impedance I have to calculate. Then for the next, it is given that the pole 0 plot is like this, there is 0, -1, and poles are at -1, -2. So if this is the information, that is real part and imaginary part j omega, so this is the situation, find the value of R and C. Okay, so let us do it. So to find out the transfer impedance V0 of s upon I of s, what can be done? First, let me calculate this I1 of s. Why I need I1 of s? To compute V0 of s. So V0 of s, basically V0 of s will be the impedance SL into the current flowing through that inductor, that is I1 of s, right? And I want I1 of s, so SL will be as it is, I1 of s will be, this is my total I of s, okay, so which is dividing in this branch and in this branch, so I1 of s will be 1 over Cs plus 1 over Cs plus R plus SL into I of s, and I'll shift I of s on right side, so left side, so V0 of s upon I of s, which will be SL into CS will cancel, so it will be S square LC plus RCS plus 1, okay, and then let me take it leading coefficient equal to 1, so it will be L over LC S over S square plus R upon LS plus 1 over LC, okay, and this will be 1 over C S over S square plus R by LS plus 1 over LC. Now again second information is given, that pole 0 plot, so from that what will be my transfer function. Zeros will at s is equal to 0, so this is s, and poles at 1 and 2, so it is s plus 1 and s plus 2. So if you solve, this will be s square plus 3s plus 2. So if you compare this denominator with this denominator which has been obtained, I have to find out what is the value of r and c. Okay, so second is r by l will be 3 and 1 over lc will be 2. L is given 1 Henry, so what will be r? R will be is equal to 3 ohm, and here L is given 1 Henry, so what is C? C will be 1 by 2 Farad. Okay, so this way you can compute the network function. You can also compute the values of R and C according to the locations of your poles. Okay, again, suppose one more thing, if I'll take, say, to the network as a current source is, let's say I'll apply this pulse with magnitude f 0 1. Okay, now this is my I of t applied to this particular network. So what is my v0 of t? If this is the question, then what can be done? Already v0 of s has been calculated which is 1 over c, so 1 over c is 2, so it will be 2 divided by s over s square plus 3s plus 2 into this. So what is the Laplace of it? It will be basically I of t will be 5 into u of t minus 5 into u of t minus 1, which is 5 1 over s minus e raised to minus over s. Okay, so this multiplied with 1 over s minus e raised to minus s over s, then this will be s will cancel, so it will be 2 divided by 5. Okay, 5 into 2, so it will be 10 divided by s square plus 3s plus 2 minus 10 into e raised to minus s over s square plus 3s plus 2, and I know the roots for this, which are 10 upon 1 over s plus 1 and a over s plus 1, b over s plus 2 minus same e raised to minus n, a over s plus 1 plus b over s plus 2, and then I can take the inverse. I can calculate a and b very quickly, and I can take the inverse. So 10 e raised to minus t plus b into e raised to minus t u of t, and this is shifting. Okay, so what will happen here? It will be, this is a1 and b1, so a1 e raised to minus t into e raised to minus n. So what will happen? There will be the shifting by 1 towards right into u of t minus 1 plus b1 e raised to minus t minus 2 into u of t minus 1. Okay, this 2 is the minus 2 into t minus 1 into u of t minus 1. Okay, so this way you can compute the response, not r of t, but it was v0 of t. Okay, so with this we stop here. We'll continue in the next class. Thank you.